Okay, I want to go over the practice test for the 13.1 through 13.3, which is the trig functions and unit circle and all that good stuff. So basically, first question, I want to explain what a radian is. So in this chapter, we introduced a new unit to measure angles other than just degrees. And basically, if you remember what we did, the way I kind of explained it in a small picture here was if you had like something like this and you had a circle going around here, and what we were talking about was standard position always talks about a measure from here, and you kind of just work your way around the circle. And what ends up happening is if you stop right here and there's a point there, and then there's an angle formed there, the idea for a radian was that the arc length, okay, so the actual like curved arc length from A to B had to equal the radius of the circle. Equals the radius of the circle. So when that happens, okay, so again, that arc length from A to B, if we were able to straighten that out, and if that was the same as the distance from A to B, which is the radius, the angle that got formed there inside here, that would be a 1 radian angle. Okay, and that kind of led us to how we got to pi radians was if you went another radius across, another arc length of a radius, and there's a point there, and then you do it again, you'd end up just shy of the y-axis the third time. So to get all the way to the 180, it was pi radians. Okay, it was just a tad past 3 radians. That was 3, that was 2. Okay, so that was kind of what I'm looking for in number 1 there. Now number 2, straight unit circle. Okay, you're going to get a blank unit circle with some quadrants that you need to fill in. Let me get rid of this ink up here. And you got to know the patterns. Okay, you just got to know this stuff. There's really no way around it. You're going to be able to tell which quadrant it is based on they're giving you the center here. So you can tell this one is quadrant 1. It's everything's kind of up in the top right. Now make sure you read through the directions. There are a lot of questions are, what goes in the box and all that stuff. So we need to list the angle in degrees and radians, okay? Then the reference angle is going to go in the box, okay? So first off, just the degrees, okay? We know the special ones are 0, 30, 45, 60, and 90. Okay. Now in this case, in the first quadrant, the reference angles are just the angles themselves. Okay, because again, we're talking about if we were to get back to the x-axis in the first quadrant, well, in the first quadrant, to get back to the x-axis is just exactly what the original angle was anyway. So these are all the same. Now, if you're in a different quadrant, the reference angles will still be 90, 60, 45, 30, and 0. It's just that the actual angles themselves may be different. Okay, like just for instance, real quick, like if this thing continued out, the actual angle would be 150. Okay, but the reference angle is just this little piece of it, theta prime, the reference angle would be 30 degrees. Okay, so just kind of keep in mind there's a difference, but in quadrant 1 they are both the same. Now the radian equivalence, again, 0 radians is 0 degrees. You got your little conversion factor that you can use. If you forget these, you can take the angle measure in degrees, times it by pi over 180. And in this case, it just ends up reducing. It's 30 pi over 180. And then the 30 over 180 gets reduced to be 1 over 6. So pi over 6. Okay, so each of the 30s is pi over 6. Okay, so that means the 60, that's 2 pi over 6, but 2 pi over 6 reduces to just 1 pi over 3. Okay, the 45, following the same kind of thing, is going to be pi over 4, and the 90 is going to be pi over 2. Okay, because again, 180 is a full pi. It's all based on that. 180 is a full pi, 90 is a half a pi. Okay, 45 is a quarter of a pi. All right, so then the coordinates now, again, this is a unit circle. So we know the radius is 1, so the coordinates of the 0 degrees are going to be 1, 0. Okay, because again, the x distance is 1, the y distance we haven't gone up or down at all. The 90 is going to be 0, 1. And now it's these middle ones that we need to kind of remember. And again, there's a lot of patterns that I've been talking about. The denominator is 2 for all of them, all the way around the whole circle. Okay, if it's not one of the borderline points like the 0, 1s and the 1, 0s, the denominators for everything else is 2. And there's a few things to remember. The 45, okay, any of the middle ones basically, your 45, or if you're in quadrant 2, it would be your 135 here. Quadrant 3 would be the 235. Those are all the same value. Those are the ones that are root 2 over 2 for both. Okay, and it really goes back to, if you want to kind of know where that's coming from, it really goes back to the special triangle, where in the one with the 45, so like let's say we had a triangle like this, and this angle was 45. If this was a 45, 45, 90, if you remember the side lengths on those, the opposite and the adjacent are both the same. Okay, so that makes like the sine. Okay, if you think of sine, like let's say we're using this 45, the sine is opposite over hypotenuse, x over x root 2. But then the cosine is adjacent over hypotenuse. So both of those are the same. They're both x over x root 2, which if you do some simplifying and cancel the x's and then multiply out the root 2, you're going to get both of these being root 2 over 2. Okay, so that's, those are kind of locked in. Now the other ones, you should remember there's root 3 over 2s somewhere, okay, and then there's 1/2s. And again, if you get stuck and you get caught up in those, think about the special triangle. Okay, if you have a 30, 60, 90, let's do the, let's find these here, the special ones for the 30. So think about this, you have like a reference angle of 30 degrees right here, and the 60's up there. Okay, the side lengths in those, okay, what I've just drawn actually is just this. Okay, just so we can kind of see what's going on. So that triangle I just pulled off to the left because here's my 90-degree angle. The side lengths on that, the short one's x, the hypotenuse is twice as long, and the other leg is x root 3. Okay, so look down here. This is the x root 3 leg. Okay, this is the regular old x leg. Okay, so what we can do is set up what would it be if the hypotenuse was 1 in a unit circle basically. So why don't we find the sine of 30. So the sine of 30 is opposite over hypotenuse, so x over 2x. Okay, we can see that simplifies to 1/2. Okay, the sine deals with opposite. You got to remember the opposite is the y value, so that is 1/2. Okay, it's the other one, it's the cosine, that if we did a similar thing over there, that would be the root 3 over 2. Okay, and then you could do something similar with the 60, but they actually just kind of switch spots. That's your 1/2, that's your root 3 over 2. So that's one good way. Now the other thing, the pattern that I think can be quite helpful too is the counting thing when I talk about counting from 0 to 4. Basically down here, let me get a different color here, let's go with the black marker. When you start out at 0 degrees down here, if we look at the y values, okay, it starts at 0, okay, and we kind of work our way up and get bigger and get bigger and get bigger, okay, and then eventually as you go around the circle they'll start to decrease, but the y values are getting bigger, so if you just count it out, think about it, this is like 0 over 2 if you wanted to think of it, since all of them have denominator of 2. The first one here is like 0 over 2, 1 over 2, root 2 over 2, root 3 over 2. Remember, 1 can be thought of as root 4 over 2. Okay, and even the first one can be thought of as root 0 over 2. So it just increases from root 0 to root 1 to root 2 to root 3 to root 4. Okay, and the x's actually do the same thing, but starting from the top. The x's follow the exact same pattern. It starts out up at 90 degrees. The x value there is 0. And as you work your way down, it's root 1 over 2, root 2 over 2, root 3 over 2, and again, that's root 4 over 2. Okay, so you kind of have all those patterns that can kind of lead you to some of this stuff. Okay, all right, so let's clear that and move on. Problem number 3 was a big table we want to fill in. Um, so I'm actually going to do this probably on another page here. But basically the thing here is they're saying for a 450 degree angle, find every single one of these. Okay, like the first thing in the table gives you theta, then they want sine theta, cosine theta, all that. Row 2 is just a different angle, and you're going to do all those things for the 7 pi over 6 angle. Okay, so that's what the table is designed to do. So let's do the 450 first. Okay, I'm going to go to a separate page here. So let's take the 450 degrees. We want to convert that into radians for the first thing in the table. So again, we're going to multiply by pi over 180, and it should end up being. You're going to end up with 5 pi over 2. Okay, a common answer I've been seeing is that people will just take the 450 divided by 180 and they get 2.5. And they say it's 2.5 pi, and technically that's not wrong, but we keep these as reduced fractions. So you're better off, remember, use the math button. Go 450 over 180, hit that math button, and have it reduce the fraction for you. Okay, because 5 over 2 is the same thing as 2.5, 2.5, but it's a lot more common to write it as a fraction like that. Okay, so that's the angle in radians. So that would be our first blank here would be 5 pi over 2. Oop, that's the wrong spot. 5 pi over 2. Now the sketch. Okay, we need to figure out where does this thing end up. I basically just want a little picture of this in standard position. So here's my XY. 450 degrees would be a full circle, and then I have to go 90 more. So I'm going to end up at 90 degrees, actually. That's going to be my coterminal angle. Right? So again, the sketch, we're going to go the full circle. There's 360 plus 90 more. So my sketch would look like that. Okay, so I'm up here. So that makes the reference angle again. The reference angle always gets you back to the x-axis. So the reference angle would be this, which would be 90 degrees. Okay, now we need the sine, the cosine, the tangent. We need all the ratios. Okay, here's where you're going to want to go to your unit circle. Okay, so the coordinates up there of a 90-degree point on your unit circle, that's just 0, 1. Okay, on a unit circle, the coordinates are the x value is always just the cosine of the angle, and the y value is always the sine of the angle. Okay, so you know 2 right off the bat. If you know it's on the unit circle and you know the coordinates, okay, that's it. So the cosine of the angle is 0. The sine of the angle is 1. Okay, tangent is always y over x, just like it has always been, opposite over adjacent. So for this problem, the tangent of the angle, okay, remember this, cosine is the x, sine is the y. So it's really just sine over cosine. It's 1 over 0, which is undefined. Okay, so that's the three the three main ratios. And we'll just go ahead and get each of their reciprocals. So let's put these over here. The one that goes with cosine is secant. All right, and if the cosine is 0, the reciprocal means the 0 is going to be in the denominator. It's going to be undefined. Okay, the cosecant, okay, the reciprocal of 1. 1 is really like 1 over 1, and the reciprocal of 1 over 1 is still just 1. Okay, now your cotangent of the angle, think about reciprocal of 1 over 0 is going to be 0 over 1, which is just 0. Okay, so those are all of your trig ratios for the 450. Okay, the next one they give you 7 pi over 6. Okay, so 7 pi over 6, we want to convert that first into degrees and then do a sketch and all that good stuff. So the 7 pi over 6, let's get a new page here. So theta equals 7 pi over 6. Okay, if we want it in degrees, we're going to times by 180 over pi. Okay, and we should end up with, if we do 7 times 180, and then divide by the 6, and of course the pi's cancel out, we end up with 210 degrees. Okay, so that's the degree equivalent. Now we can go ahead and sketch the angle. Okay, sketch just means throw it in standard position, see where it ends up. Okay, so I know I always start positive x. If that's 180, I need to go a little bit past. Okay, so there's the sketch. Now my reference angle is always back to the x-axis, no matter what. So it's the x-axis and where the angle ends. That angle there is theta prime. Reference angle in this case, since we went out to 210, that means we went 30 past 180. Okay, do a little subtraction problem. There's your reference angle, theta prime. Okay, and now we can go ahead and get the sine, cosine, tangent, all the trig ratios. Now remember, we're doing this based on the 7 pi over 6. Okay, the point on the unit circle is down here in quadrant 3. Okay, now you can use the values from the 30 degrees, but for our actual angle, they're both going to be negative because the x's are negative and the y's are negative in quadrant 3. So if you go on your unit circle, okay, down at 210 degrees here, okay, remember the coordinates there are the y value is negative 1/2, and the x value is negative root 3 over 2. Okay, they're the exact same as what the 30 was. It's just that at the 30, they were both positive. Okay, so here's your cosine of your theta. Okay, the y value again is just your sine. Remember, that's just the opposite side length. The sine of the theta is negative 1/2. Okay, and if you don't want to write theta in here, we could have written like the 7 pi over 6, what they gave us the angle to start with, but that's fine. Okay, now we got to do a little bit of work. Tangent is, again, y over x. Okay, think about it. It's opposite y over the adjacent, which is x. So it's sine over cosine. So negative 1/2 over negative root 3 over 2. Okay, and since it's a fraction divided by a fraction, okay, tangents will usually be a fraction over a fraction for the most part. We got to multiply by the reciprocal of the denominator. Okay, so what ends up happening there, the 2's will cancel. It ends up being negative 1 over negative root 3. So again, if they're both negative, we'll just make it positive. And we do want to go ahead and rationalize, times by root 3 over root 3 just to simplify that denominator. So we should end up with a root 3 over 3 for tangent of theta, and it's positive in this case. Okay, it was a negative thing divided by a negative thing. The answer is positive. Okay, and then just the reciprocals real quick. We could do secant is going to be the reciprocal of this guy, so 2 over negative root 3. Now we do need to multiply again. Multiply by root 3 over root 3. Okay, so 2 root 3. The negative root 3 times negative root 3 is just negative 3. So there's your secant. Okay, cosecant is going to be the reciprocal of sine. So just flip that over. Luckily there's no roots in there, so it's just negative, or it's just 2 over negative 1. So it's actually just negative 2. And then cotangent of theta is going to be the reciprocal of tangent, so 3 over root 3. Okay, and that needs to be simplified a little bit, so times the root 3 over root 3 just to rationalize, and that'll give you 3 root 3 over 3, but then of course the root 3, or the regular 3 over 3 cancels, and we just get root 3. And there is your 6 trig ratios for the 7 pi over 6. Okay, so we would just organize those, fill those in the table, and that would be that. Okay, question 4, they want you to derive. It means like show where they came from. The exact values for the 3 common, so just sine, cosine, tangent, for a 60-degree angle. Okay, so if you remember, those came from the special right triangles. Okay, so the question's either going to be a 60, a 30, or a 45. So this one's about the 60. So let's draw 30, 60, 90. Again, some people draw them differently, but the key is we need a short leg and a long leg. Okay, now if it had been a 45, 45, 90, you would have to draw both legs the same, so something like that. Okay, but that's not what we want for this problem, but it might be on the test that way. So just be clear, when you draw them, you want to be kind of clear so you can start labeling sides and they can seem like they fit. So like here's a short side, X, so that has to be the small angle. Okay, and then we got the 60 degree and then of course the 90. So you got to know these side lengths. It's X. The longest side, the hypotenuse, is twice as long, and the middle length is root 3 as long. Okay, and just kind of remember, root 3 is about 1.71 something. So you can see clearly the 2x is longer than root 3x. Okay, so now to derive these three, just the three main ones, again, we're using the 60 here because that's what this problem wants. So this side over here is the opposite. That bottom x is the adjacent, and then we have the hypotenuse over here. Okay, so if we go ahead and set these up, the three main ones, sine of 60 degrees, opposite over hypotenuse, x root 3 over 2x. Okay, your x's cancel out, it's root 3 over 2. Okay, that's the sine of 60. Okay, if you go to your unit circle, 60 degrees, the y value is going to match up with that, root 3 over 2. Okay, so this is another thing. If you forget when you're filling out the unit circle, as long as you know how to do this, you can get the y value. Okay, so again, let me just kind of connect the dots here. In the unit circle, again, the 60 degrees, what we just found would be the y value up there. Okay, that's the sine of 60. All right, the cosine of 60, oh, way too far. There we go. Okay, the cosine of 60 degrees is going to be the adjacent over the hypotenuse. Okay, adjacent is x, hypotenuse again is 2x. Okay, and 1x over 2x reduces to 1/2. And then the tangent of 60 opposite over adjacent, so x root 3 over x. Okay, the x's cancel out. The tangent of 60 is root 3. Okay, number 5. Given an angle in standard position with terminal side passing through -3, -2, complete the following. Okay, so they're giving you some coordinates. They're giving you an x and a y. Okay, now we don't know if this is on the unit circle. Okay, in this case it's probably not, because again, if it's on the unit circle, the x squared plus y squared needs to be 1 to get the radius. And this one I can kind of tell those numbers are a little big. So let's think about what we know. We know we're at -3, -2. Okay, there's a point there. That point is roughly here. Okay, they're telling us something important. It's on the terminal side of the angle. So the angles always start here. It's telling us this one ends going through there. Okay, so that whole big thing is our angle. So if you want to think reference triangle's there, where theta prime would be here. Okay, now they gave you the side lengths. They gave you two of them actually. They gave you the x and the y. Okay, the x value, that's -3. The y value is -2. Here's my reference angle. So they gave you an opposite and an adjacent basically. We just need to know the hypotenuse. Okay, and that's kind of what we had been calling r. So that would be a good thing to find first, a little Pythagorean theorem. Okay. Okay, so again, x is -3. Y is -2. Okay, so that's 9 plus 4. So r squared is 13, so r is going to be the square root of 13. That's our hypotenuse there. Okay, and just leave it like square root of 13. It doesn't need to be a decimal. It doesn't need to be a whole number. Okay, we know the square root of 14 somewhere between 3 and 4. That's fine. Let's leave it exact. Okay, so now we know x, we know y, and we know r. Okay, so we can go ahead and write all of these trig ratios. Okay, or you can just think of it as a triangle now where you know all the sides. Okay, if we want the cosine of theta, it's adjacent over hypotenuse. Okay, the thing is the adjacent is the x value. The hypotenuse is the r value. Okay, x over r. So if we just rationalize that, times root 13 over root 13, we will get negative 3 root 13 over 13. There's the cosine of theta. Okay, what about sine theta? Opposite over hypotenuse. Okay, the opposite side from the reference angle is the y value. That's why sine is always y over r. Y over r. Oops, it needs to be a square root. And we'll rationalize that one the same way, times top and bottom. Okay, so negative 2 root 13 over 13. Okay, tangent, the tangent of our angle, y over x. Opposite over adjacent, y over x. Tangent of the angle, negative 2 over negative 3, which is actually just equal to positive 2 over positive 3. Okay. All right, let's go ahead and get some reciprocals. So we need all 6 here. We need the reciprocal of secant. That goes with, I'm sorry, the reciprocal of cosine goes with secant. That's just the reciprocal of cosine, right? And cosine was originally that. Its reciprocal is going to be its reciprocal. The root negative 3 goes on the bottom, root 13 is on the top. Okay, so I would use that one. I wouldn't use the one in blue here because then when we do the reciprocal of that, the root 13 is going to go on the bottom and we're going to have to simplify it. Okay, so the thing I wrote in red, that's the cosine also, right? So let's use that one. So for when we want cosecant, it's the reciprocal of sine. This in red here is sine. So its reciprocal is this. Okay, and then of course the cotangent will be the reciprocal of tangent, so 3 over 2. And there's all of the ratios. Okay, now the question part C wants to know what is theta, how big is the angle. Okay, so the actual angle is this. Okay, how big is that? So what we could do there is use an inverse trig ratio, or function I should say. So think about, we know the tangent of theta that we just did right here is equal to 2/3. Okay, if we want theta, we need to do the inverse tan on both sides. So let's go inverse tan, inverse tan. Okay, so that's going to cancel that and just give us theta. And so we need to go in our calculators, make sure we're still in degree mode here. I'm going to do tan negative 1 of that fraction, or inverse tan of that fraction. Okay, let me check my calculator. I am in degree mode, so inverse tangent of 2/3 gives me the angle measure of around 33.7 degrees. Okay, so that seems like that should be our answer. Okay, now you gotta be a little careful here. Does it look like our big angle theta is 33.7 degrees? No. Okay, we're in the third quadrant. I know the angle's between 180 and 270. So what they actually found, what we actually found, this is actually the reference angle. Okay, so that is actually this piece. So our actual red angle theta is 180 plus that. Okay, because again, we had to go from the center all the way down to there. So if you add 180 to that, that should give us our answer. So we should be around 213.7 degrees. Okay, so just kind of think it out. 33.7 seems like we did everything right, but again, that's the reference angle. Okay, number 6. Going back to the first section here, 13.1. Just the SOHCAHTOA right triangle stuff. So we got to solve the right triangle, means find everything. Okay, so I'm going to eventually need a capital A for that angle. I need a lowercase b for the side length and a lowercase c. Okay, we kind of know that angle's the 90, or we can assume. So what I could do, you got a lot of things to use here. You have SOHCAHTOA, you have Pythagorean Theorem, you have angle sum of 180. Okay, so I would think the angles would be easiest if we know 2 of the 3 angles, and I know they all add up to 180. So this one up here should have to be 25 degrees to make that, to make that happen. So we know angle A. Now we know one of the three sides, and we got to find the other two. So a trig ratio could do that. So couldn't we say something like, if I'm using this angle, and let's just say I'm just choosing to find A first. You know, you got to find A and B, pick one. So couldn't I say that from the 65, this would be the adjacent side, that would be my hypotenuse. So couldn't we say something like the cosine of 65 degrees is the adjacent side over the hypotenuse? So cosine 65 equals this unknown A over 9. And we're trying to solve for A, so there's a 9 in the denominator. If we multiply both sides by 9, okay, 9 times the cosine of 65. Again, just a calculator problem. Make sure we're in degree mode. This on my calculator is 3.8. Okay, and we'll just say approximate because we rounded a little bit. Okay, so A would be 3.8. Okay, and now we can go ahead and find B. So you have options. You can either use Pythagorean Theorem now. All right, because think about the picture. Now we know two of the three sides. We know that's 3.8. We know that's 9. We just don't know that one. You could go ahead and do Pythagorean if you want. Or we could use another trig ratio. Let's just do a trig ratio just to, since that's the topic here. So again, that angle was 65, so that's the opposite, and 9 is the hypotenuse. So I could use sine. I could say the sine of 65 degrees is the opposite over the hypotenuse. And it's a very similar problem. It just uses sine instead of cosine. But same exact steps to finish it out, isn't it? When we just multiply again, there's a 9 in the denominator. Times by 9, get rid of that. Times by 9. So if we just do 9 times the sine of 65, we will get around 8.15, so 8.2 approximately. If we want to round to the nearest tenth like it wanted. Okay, so there's your A, your B. We got all the angles, we got all the sides. We are good to go. Okay, and then the last couple, they give you a couple kind of word problems where you got to set up a picture and put some information into a picture. So how tall is a flagpole? So measuring 10 meters from its base. So again, we're kind of assuming here's the ground, here's a flagpole. We're measuring 10 meters from the base. So from there to there is 10 meters. Okay, the angle of elevation. Angle of elevation is always the measure from the ground to the top of the unit. So again, this is the ground down here. The angle to the top is 75 degrees. Oop, a little sloppy there, but that's supposed to be 75 degrees. And we want to know how tall is this thing. So that's like our x. Okay, so again, it looks like from the 75, it looks like we are dealing with an opposite side and an adjacent side. Okay, the hypotenuse over here doesn't really affect us in this problem. So let's use tangent, opposites and adjacents. Right? Tangent is 75, opposite over adjacent, x over 10. Okay, so just like the last problems we did, actually, just multiply both sides by 10. So 10 times the tangent of 75 is about 37.32. Okay, nearest tenth of a meter, 37.3 meters. Okay, so that's that. All right, number 8, a zip line. So that Z for zip line will be run from a 100-meter tall cliff down to a platform 10 meters above the ground. So it's a 90-meter drop. Okay, so it seems like if this is our picture, there's like this platform here, and the drop is 90 meters. Okay, the whole platform is 100, but to where we're dealing with is 90. Okay, so there's a little 10-meter platform here, but that side of the triangle is 90 drop. The angle of elevation at the bottom is 20 degrees. Okay, so again, that's going to be this angle here is 20 degrees. And we are in need of the length of the zip line. Okay, so our triangle, let's just kind of draw this a little nicer here. 20 degrees, 90, we want to find that. Okay, so again, this one looks like an opposite and a hypotenuse. Okay, so a sine problem. So the sine of 20 degrees will equal 90 over x. Okay, now this one's a touch different. The variable's in the denominator, but whatever's in the denominator you're going to multiply by. Get it out of the denominator. Times both sides by x. Okay, so we have x times the sine of 20 degrees equals 90. Okay, so to get x by itself, we will have to divide both sides by the sine of 20. So this had one more step than the other problems because the variable was in the denominator. Okay, but again, notice that cancels that. So x equals, you're going to go in your calculator, 90 divided by the sine of 20, and that should give us an answer. And if we round that to the nearest tenth, let's take that down here, x, or I guess in this problem it was z, is going to be around 263.1, what's our unit, meters? Okay, and there is your answer.